compression refrigeration system. You see the name Vapour. Already we have studied the air refrigeration cycle. Air refrigeration cycle we have studied. So now this cycle is the Vapour compression refrigeration cycle. You see. So after reading, after analyzing this chapter, the objective, the specific objective is you will learn Carnot refrigeration cycle. Carnot refrigeration cycle, here also it is there. Then standard Vapour compression refrigeration system. And we'll analyze the standard Vapour compression refrigeration system. Learning outcome. Analyze and perform cyclic calculation for Carnot refrigeration system. State the difficulties with Carnot refrigeration cycle. There is a why Carnot refrigeration cycle is a only standard one. This is not practical one. Then analyze and perform cyclic calculations for standard Vapour compression refrigeration system. And if you'll able to perform various cycle calculations for different types of refrigerant. So different type of refrigerant already we have studied. There are different types of refrigerant, that is R11, R12, R22, but they are now obsolete. Previously, R12 was used extensively. So before 2006 in India, in all the windows, all the household refrigerator and the air conditioner. But due to ODP, ozone depletion potential, that is, it creates the ozone hole. The stabilized CFC create ozone hole. Due to this, there is a Montreal protocol here. It was decided to remove all these refrigerants which have high ODP value, and they are replaced by another low ODP value. Although they are very good refrigerant in terms of thermodynamic property. So physically nowadays we are using 134A in most of the refrigerator. 134A. Now, what is 134A? 134A actually it is a tetrafluoroethane. If you analyze, now you know what is 134. Now you can find out what is the chemical formula. Its chemical formula is C2H2F4. This is the chemical formula. So we can write it as CF3 CH2F. This is the chemical formula. So from 134, in the last class, we calculated how 134 comes out to this chemical formula. Okay. Now the next one is so here we are writing A. So whether 134 R134 and R134 is same. See, generally the term A word is used for isomer. Actually, R134 and R134A is two different compounds, but they have the same chemical formula. What is the meaning of isomer? Isomer have the same chemical formula, but they have some different physical property. Now, R134 has the normal boiling point minus 19 degrees centigrade. This is the property. But R134A, its normal boiling point is minus 26 degrees centigrade. Both has the same chemical formula, that is C2H2F4. But this term A is used. It is different from here. It is an isotope of 134. Sorry, it is an isomer of 134. Remember. So nowadays we are using 134A. But remember, don't write capital A. Capital A, don't write. It is a wrong. You have to write a small a. If you write capital A, it will denote it is a non-azeotropic refrigerant. Okay. If you write capital A is a symbol used for designating non-azeotropic refrigerant. Remember. So in this case, you have to write A. A stands for isomer. Means it is the same chemical formula with 134A but different property. Okay. Now again, there is a term where I'm telling you this is a non-azeotropic. So the question is, what is azeotropic? Azeotropic. Now you see, azeotropic refrigerant is a mixer. It is a mixer of two or more component. It is actually, it is not a single component. It is a mixer of two or more components. Okay. But these two components, you cannot mix any two. They have certain property that boil at the same temperature. That is, they are at same temperature. That is, the two components you mix, they should have the same boiling point. They are different components, but their boiling point is same. Then if you mix them and form a new component, then this is called the azeotropic refrigerant. Already we have studied a air refrigeration cycle, gas cycle, that is a air refrigeration cycle. And the next one is the vapor cycle. You see that word vapor. What is the difference? In case of gas cycle, already have studied, or in case of air cycle, in all this process, there is a no phase change, no phase change. Only air temperature, only temperature goes up or temperature goes down. Only temperature goes up and in certain portion of the cycle, temperature goes down. That means there is a only sensible heat transfer. You see the word sensible heat transfer. So there is only sensible heat transfer in such type of cycle. As a result, the heat transfer capacity is very small, because you see always for higher rate of change of the temperature, there must be latent heat transfer. This term, latent heat transfer. So in case of sensible heat transfer, there is a no phase change, but in case of latent heat transfer, the phases changes from liquid to vapor or from vapor to liquid, like this. Now in case of this cycle, vapor compression cycle, they are using, suppose there is CFC, mainly they are using CFC. Okay. So they are in two phases. During this cycle, they are in two phases. In one part, they are vapor, and some other portion of the cycle, they are liquid. Okay. So while it changes phases from liquid to vapor, there is a latent heat transfer. As a result, high mode of heat transfer takes place. So this is the difference. You see, in a vapor cycle, the working fluid undergo phase change. You see, this is the most important part, where there is a no phase change in air refrigeration cycle or gas cycle. And refrigerating effect is due to the vaporization of refrigerant liquid. You see, here refrigerating effect is due to the vaporization of refrigerant liquid. That means due to the latent heat transfer. But in case of air cycle, the gas only sensible cooling. That is why the required mass flow rate for a given refrigeration capacity will be much smaller compared to the gas cycle. The required mass flow rate. As more heat transfer takes place in latent heat in case of vapor compression cycle, so very less amount of mass flow rate requirement is very small. And that is why we are getting the COP for this vapor compression cycle is very high. Now, in our domestic refrigerator, you see, in your domestic refrigerator, the main cycle is the vapor compression refrigeration cycle. Vapor compression refrigeration cycle. It is this one, where generally R134A refrigerant is used, and during this cyclic process, R134A changes its phase from liquid to vapor during the evaporation process. As a result, latent heat transfer takes place and a huge amount of heat is extracted. Okay. Actually, this is the photograph on the back side of your domestic refrigerator. Domestic refrigerator. Nowadays, the refrigerator is in a closed unit, but if you see in your back side of the refrigerator, there are some, this is called fin, this is cycle, and at the bottom, back side at the bottom, you will see this assembly. And this is fan, extra fan is used, and this is the compressor. This is the compressor. In case of vapor compression cycle, the cycle is there is a compressor. This is the compressor. After that compressor, there is a condenser. Now, condenser. After condenser, there is a expansion valve. Expansion valve. No turbine, remember, expansion valve. And after expansion valve, there is a evaporator. Evaporator. After that, again, it goes to the compressor. Now, evaporator, in the evaporator, your refrigerating effect takes place. Refrigerating effect. That is the working fluid now changes from liquid to vapor here by extracting heat from your commodity, that is in the freeze. In the freeze, you have different foodstuff, different vegetables, and different products. And the refrigerant, which is in the liquid state at this point, now takes heat from the commodity in the freeze, and it converted to the vapor. That means there is a latent heat transfer. As a result, huge amount of cooling you will get. And after that, it converted to the vapor and it to the compressor. Now, in these cases, so this is only the compressor unit. You see, there are 4 units: compressor, condenser, expansion valve, and then evaporator. And this is a 1 unit compressor. This is the compressor here in the cycle. And the name of this compressor is a hermetic compressor. What is the difference between this compressor? And this hermetic compressor, actually inside the compressor, there is a motor. And this motor is coupled with this compressor. And all are housed in a single assembly. This is the assembly, steel assembly. You see, this compressor is run by the motor, and which are enclosed in a welded steel casing. And both are connected by a common shaft. So this is called hermetically sealed compressor. What is the difference between the general one? In case of general compressor, this is the compressor. This compressor is coupled either in a motor externally, or by belt, or the compressor it is connected by belt, etc. So this is the difference. And you always remember, all the domestic refrigerator, they have such type of compressor, hermetically sealed compressor. Okay. Now you see, this is the block diagram. You see, this is the compressor assembly. This is the compressor assembly, and this is the suction pipe. Here, freon gas. Now it is freon. It enters here. Enters. Now this is the entering, and it will enter in the compressor. You see, the compressor is coupled with a motor through crankshaft. All are housed in the same assembly. Now motor is run by your AC voltage. Okay, motor is run by external, that is your electricity, and it is sucked. During this process, it is sucked, the freon gas, and then during this stroke, this is compressed, and so you will get a high pressure and high temperature freon gas at this point. So in your cycle, this is the inlet of the compressor and this is the outlet of the compressor. After that, it will enter to the condenser unit. It will enter to the condenser unit in the cycle. And after condenser, it will go to the expansion valve, where expansion takes place, temperature and pressure drops. And after that, this low temperature and low pressure refrigerant enters to the evaporator, where refrigeration effect takes place. Again, that it convert to the gas, and that gas enter to the here. So this is the cycle. Now we'll analyze the cycle, Carnot refrigeration cycle. Here you see in Carnot refrigeration cycle, there is a compressor. This is the condenser. This is the condenser. This is the compressor. Then this is the turbine, or we can say expansion valve, and this is the evaporator. Evaporator means here the refrigeration takes place. Now first try to understand what is the meaning. This is called vapor dome. Vapor dome. Here this is the TS diagram, temperature, entropy diagram. And this is the vapor dome you see. Now in this curve, left hand side of this curve, all are liquid. Again, right hand side of this curve, all are vapor. And in between these two points, it is a mixture of liquid and vapor. You see, if your point is in this point, so this is the liquid and vapor. Now you see here, this is a mixture of liquid and vapor, point 1. Here, it is a mixture of liquid and vapor. After that, it enters to the compressor. Compressor compresses and it converted to a dry vapor. Remember, this is not a superheated. If it enter in this direction, this is a superheated vapor, and this is a dry vapor. Dry vapor. Okay, it is a dry vapor. So this is the position. After that, it enters to the condenser. So heat is rejected to the other medium. That is, in your domestic refrigerator, this other medium is atmosphere, air. Atmosphere. That is why your backside you should keep a distance around 1 feet from any obstacles. In your domestic refrigerator, you should keep it place your backside. And nowadays, from the side, the condenser is in the side also. You see, if you put your hand there on the side, it is a closed unit. You'll see it is a hot. So that is condenser. There should not be obstacles. Okay, so it rejects the heat. Now it temperature. So this is in this case. Now this is the point 3. So it becomes the liquid in this case. So this condition is liquid. You see here, this is a vapor. Here it converts to the liquid. In the liquid, this is a turbine. So expansion takes place. It is isentropic expansion. So in the turbine, and it becomes a mixture of liquid plus vapor. And now here the mixture liquid plus vapor, and the liquid convert to the more vapor. That means there is a latent heat transfer. You see, temperature remains constant in this process. There is no sensible heat transfer, only latent heat transfer, because the liquid convert to the vapor. In here you see in this position, the percentage of vapor increases. Percentage of vapor increases. Okay. So this is the Carnot cycle. Carnot cycle, it is not a practical one. Why not a practical one? You see, this is an isentropic compression. In general, isentropic compression is not possible. There again, this is an isentropic expansion process in the turbine. It is also not possible. The second point is, In this case, you see, here this is the entry point of the compressor. The compressor has to deal with a mixture. You see, the compressor has to deal with a mixture of liquid plus vapor, because the liquid droplets, it may break the compressor blade. So, and the second point is that compressing a liquid is very difficult. Liquid compression is very difficult. Okay, then the vapor. That is why here it is very difficult to compress a mixture of liquid and vapor from the point 1 to 2. Similarly, again you see here also in expansion valve also, it has to deal with a mixture of, this is a turbine. Again, turbine has to deal with a mixture of liquid and vapor. So this process is also very difficult. Now how it is difficult, we see. So practical difficulties. During process 1 and 2, that is the compression process, a mixture consisting of liquid and vapor have to be compressed isentropically in the compressor. Such a compressor is known as wet compressor. And always remember, as an engineer, the wet compressor is very much difficult. And wet compressor means presence of liquid. In practice, wet compression is very difficult, especially with reciprocating compressor. The problem is particularly severe in case of high-speed reciprocating compressor, which get damaged due to the presence of liquid droplet in the vapor. So this is the problem during the process 1 and 2 during the compression process. The next one is, you see, during the second difficulty is that during the process 3-4. 3-4 process means during this process, 3-4, this process. Again, the turbine. What is the difficulty? The second practical difficulty with Carnot cycle is that using a turbine and extracting work from the system during the isentropic expansion of liquid refrigerant is not economically feasible. Why it is not economically feasible? You see, the work done in a turbine, we can write PE, that is the evaporator pressure, to the compressor pressure, VDP. This is the formula. Now, in case of heat, this is the volume, specific volume. The specific volume of liquid is much smaller compared to the specific volume of vapor. That is why work done, work generated by the turbine is very, very small. And that work is not sufficient to run the compressor. You see here, this turbine work is transferred to run the compressor. But this turbine has to deal with liquid. You see, here this is the liquid. The liquid has to compress, it has to expand. So your integration of VDP, this is the work done in the turbine from this pressure to this pressure. So this V is the specific volume of liquid, and specific volume of liquid is very small. As a result, this integration is very small. This is very small, and for which reason the work generated by the turbine is very small.